Okay, so we're going to continue our discussion of section 5.3, and we were looking at logarithmic differentiation. And remember, the way that we're going to find dy dx with logarithmic differentiation is a process that is going to be given by these steps. First of all, we're going to take the absolute value of both sides of the equation. So typically we have equation, y equals something. But anyway, so we're going to take the absolute value of both sides. Then we're going to take the natural log of both sides. And then once we have that, we're going to use our log rules to make life a little bit easier for when we take the derivative. And then after we do that, we're going to take the derivative of both sides with respect to x and find dy dx by implicit differentiation. All right, which we did in the previous section. Okay, so let's go and remember what's implicit differentiation. That's nothing more than the chain rule, right? Okay, so let's go back to the example that we were working on. And anyway, this is an example that's in the book as well. But anyway, we had for the example that we were working on, we had y equals the cubed root of x plus 1 over the square root of x plus 2 times the quantity x plus 3. Now, if we're going to find dy dx for this, we could actually, use the quotient rule, and within the quotient rule in the denominator we have a product. We could use a product rule, but within all of that you have to use the chain rule because it's a quantity to a power, that type of stuff. And so we could do all that and verify and get the exact same result as what we're going to get with logarithmic differentiation, but I will tell you it's going to take you 20 minutes to verify it doing it the way we did stuff in chapter 1. So ultimately we're trying to have some time saving going on here with logarithmic differentiation. So the first step we said is take the absolute value of both sides. So we're going to do that, and remember the absolute value of a fraction, a over b, is the absolute value of a over the absolute value of b, and of course then on the bottom the absolute value of a product is the product of the absolute values. So we can split it up this way, and then what we can do now is take the natural log of both sides. So if I'm going to take the natural log of both sides, we've got this. So of course it's the natural log of this whole quantity over here. And now I can use log rules on the right. So basically what I'm going to have is a natural log of the absolute value of y is going to equal, remember the natural log of the quotient is the difference of the natural logs. So we can say it's the natural log of cube root. And in fact, I'm going to write this as a power now. So, whoa, I don't know what that's doing. Natural log of x plus 1 to the 1/3 power, and then minus the natural log of the product. Okay, so the natural log of the product is the sum of the natural logs. So remember, I'm this is a quantity on the bottom, and so once again I'm going to write x plus 2 to the 1/2 power. I'm going to write it in power mode, and then plus. So the natural log of the product is the sum of the natural logs. Not sure if I said that right or not. Plus the natural log of the absolute value of x plus 3. So basically we're using log rules to rewrite this. And then what do? Then we're going to take the derivative of both sides with respect to x. And when needed, we're going to use implicit differentiation. So anyway, derivative of the natural log of the absolute value of y is 1 over y, but then what? Times dy dx. Since there's a y there, we got to use implicit differentiation because y is some function of x. So we have that on the left side, and then on the right side, I'm gonna go ahead and I'm gonna add the opposite through here so that we have that. And then, so we have the natural log of a function. Of course, what can I do? Could I use log rules here? Could I drop that 1/3 down in front? I could. I could also do that here. I could drop that 1/2 down in front. So this is actually minus 1/2 in front there. Okay, and then this one is just to the first power, so we're fine there. So anyway, the derivative of a constant times a function is the constant times the derivative of the function. Derivative of natural log of something is 1 over that something. So 1 over x plus 1, but then times the derivative of what's inside. By the way, when I did this on the board, I did not drop that 1/3 down in front. I don't know why, because this is going to make life so much easier. But anyway, what's the derivative of what's inside by the chain rule is just a 1. So the derivative of x plus 1 is 1. But if that was like 3x plus 4, then I'd say times 3 here, right? Anyway, and then minus 1/2. The derivative of natural log of something is 1 over that something. So it's 1 over x plus 2. And then times derivative of what's inside, so times 1 here as well. And then minus the derivative of the natural log of 1 over x plus 3, or excuse me, x plus 3 is 1 over x plus 3, so 1 over that, times the derivative of what's inside, so times 1 again here. So the time ones don't really matter, so instead of trying to rewrite this, I'm going to see if I can just erase these now. So anyway, get rid of the times 1 there. All right. So we have this, and then what I can do now is kind of rewrite this a little bit, but ultimately I want to show you that, use a different color here. What haven't I used yet? Let's use black. This y here, what can I do to both sides? I can multiply both sides times y then. And then so dy dx is going to equal y times this quantity over here. So I'm going to go ahead and we can rewrite these over here as 3 times this, and then minus, 2 times that, and then minus 1 times that, and then use the eraser here. So let's get rid of one of these. I think I had the erasers. Get rid of one of these ones on top. Come on. Okay, so kind of making it look a little better over here is what I'm trying to do. And then go back. So basically, I've got 1 over 3 times the quantity x minus 1, 1 over the quantity 2, or 2 times the quantity x plus 2, and then minus 1 over x plus 3. And I'm going to take y times all that, and that's going to end up equaling dy dx. So let me get a new screen here. And then, so we're going to, that implies that dy dx then is y. What was y? Y was the original problem, which was the cubed root of x plus 1 over square root of x plus 2 times x plus 3. That was y. So this is y that we had before, and then times what we had left, which is 1 over 3 times the quantity x plus 1 minus 1 over 2 times the quantity x plus 2, and then minus 1 over the quantity x plus 3. So there we go. So no need to multiply that out. This is good enough for the answer as far as I'm concerned, and a very quick, easy process on how to get there. I'm not sure what's going on over here. Okay. Anyway, so that's logarithmic differentiation. But I will tell you, if we try, and maybe we can do it in class real quick or something too, but if you try to do the quotient rule and the product rule within the quotient rule, then life gets a little bit challenging for something like that. So anyway, logarithmic differentiation is a very nice process. that we can use to come up with derivatives. Okay, so now let's we looked at a couple other examples where we use substitution. So now let me go on to maybe there's an odd or something that we could do. Let's do an odd here. Well, let's do a couple odds. Let's look at number 9. Number 9 is kind of a nice one because we've got y equals x squared times x squared minus 1 quantity cubed times x plus 1 to the 4th power. So if we have something like this, and I want to find dy dx, so that's what we're trying to do, find dy dx. Okay, if I'm going to use chapter or calculus 1 methods back in chapter 2, I've got to use the product rule twice, and this gets very lengthy and very involved. So what I'm going to do is I'm going to try this using logarithmic differentiation. So I'm going to take the absolute value of both sides. Of course, absolute value of the product is the product of the absolute values. So we have those rules there. So we have this, and then I'm going to take the natural log of both sides. And then on the right side, so that's natural log of that quantity. On the right side, I'm going to have log rules that I use. So the log of the product is the sum of the logs. So anyway, this becomes natural log of the absolute value of x squared, which I don't need that absolute value, right? And then plus the natural log of x squared minus 1 quantity cubed, and then plus the natural log of x plus 1 to the 4th power. Okay, now these were actually absolute values there, right? So this one is to the 4th power, so that's going to make everything positive, so we're fine on that. This one is cubed, so we could have negatives, so we should probably leave these absolute value bars there. Now what I'm going to do is I'm going to take the derivative of both sides with respect to x. And if I do that over here, I get, this is just 1 over y dy dx. So notice the pattern there when it's just y equals something in terms of x over here. So I was going to end up this way on the left. But anyway, then what we have here, derivative of the natural log is 1 over. So this is 1 over x squared, but times the derivative. Actually, what I could do first is I could drop these down in front. I didn't do that either. So let me do that. So this is, I'm going to rewrite that in blue underneath. This is 2 natural log x plus, I can drop this 3 down in front, make my derivatives a little easier here. Natural log of the absolute value of x squared minus 1, and then drop that 4 down, and then plus 4 natural log of x plus 1. And I don't need these absolute values because I didn't need them up here. So anyway, so let me redo this. Basically, what I would have got if I didn't simplify this is 1 over x squared times 2x, right? And then the x's would cancel out. But instead of that, I thought I had my eraser. Now what I'm going to have is a little easier version of this. So this is 2 natural log x, so it's 2 times the derivative of natural log x is 1 over x, right? So just 2 over x. Well, that's what I would have got if I would have used this, because I would have had 1 over x squared times the derivative of x squared, which is 2x, and it would have simplified to this. But by dropping that exponent down, utilizing your log rules is really what we want to do on logarithmic differentiation. Then I'm going to get just 2 over x. And then the rest is pretty basic. Once again, I'm taking the derivative of the simplified version here. So this is 3 times what? Well, the derivative of the natural log is 1 over x squared minus 1. And then times the derivative of what's inside, well, that's 2x. Okay, So times 2x by the chain rule, right? And then plus 4 derivative natural log of x plus 1 is 1 over, and then derivative of what's inside is just 1, right? So we have this, and then, of course, I could rewrite 3 times 2x and rewrite that as 6x here, right? Things of that nature. And then what I'm going to end up with here then is I'm going to multiply both sides by y. So dy dx is going to equal y, which what was y? Y was x squared times x squared minus 1 quantity cubed times x plus 1 to the 4th power from up here, the original, before I put the absolute values on it. So that's y times the purple function here. So 2 over x plus 6x over the absolute value of x squared minus 1, and then plus 4 over x plus 1. And then, of course, we can look at the back of the book to verify that that's all correct. But that's dy dx. So versus trying to do the product rule multiple times and the product rule within the product rule and all that, trying to combine like terms and verify that's the same, logarithmic differentiation is a much, much quicker, easier process to help us get a derivative. So a very nice tool that we now have in Calc 2. So let's look at number 25. Once again, this is on section 5.3, page 457 in our book. This would be the antiderivative of 2x cubed over x squared minus 4. See if we can do this with respect to x. So I just pulled this out of the hat live. So this is just your professor trying to figure this out. Well, this is a little bit awkward here. It'd be nice to substitute this, right? So sometimes, you know, you may say, hey, I want to let u equal x cubed. So we could do that. If I let u equal 2x cubed, let's try this. What's du equal? Du would equal 6x squared dx. So, but we got to be a little bit careful. This is an x squared dx, but what do I have? This is on the bottom. So this not only is the x squared on the bottom, it has a minus 4 there. So this doesn't really work very good. So let's try this a different way. So let's let u equal x squared minus 4, and then what's du equal? Du would equal 2x dx. Well, I could rewrite 2x cubed as 2x squared times x, and then dx. So the x dx here, I could replace that with du over 2. So let's rewrite what this is equivalent to. So that'd be du over 2. I can take that 1/2 out front. And of course, I still have, that was hard to see here, but I have a 2 here as well. So I could pull that out front, and then that's 2 over 2. Well, guess what? Those cancel out. And what am I left with? I'm left with x squared over x squared minus 4. But x squared minus 4, I can replace that with a u, right? So I'm going to go and get my eraser out. I'm going to replace this with a u, which is what I wanted there. But then I still have an x squared on top, and that's a little bit of a problem because how do we get that? Well, here we go. I'm going to use a different color here. So for this x squared, I need to make that in terms of u, right? I'm putting everything in terms of u. So here's my x squared. I can use this top equation here and say, hey, this implies, just add 4 to both sides, x squared equals u plus 4. And so if I do that, then x squared equals u plus 4, then this I can replace with u plus 4. So now what's my antiderivative equivalent to? It's going to be whoa, come back here. It's going to be equivalent to the Oh no, it's not letting me write. Come on. Antiderivative, I'm getting locked out on the drawing capability. But basically, I can rewrite this original antiderivative using substitution the second way of the antiderivative of u plus 4 over u du. And then now what I can do is I can divide each part by u. So u divided by u plus 4 divided by u. Of course, u divided by u is 1. Antiderivative of that will just be u. And then antiderivative of 4 over u is 4 times the natural log of the absolute value of u, and then plus c, and then back substitute in. So that's kind of left to the reader for you to finish up and figure that out. But I gave the process here, so I am going to go try and X out of this and then come back in, see if I can finish it. So I'm going to leave and come back and hope that works. And of course, every time I've got to make sure that I can talk. So anyway, I had x squared minus 4, that's my u, and then plus 4 natural log of the absolute value of x squared minus 4, and then I'm just going to say plus c1, and then that minus 4 plus c1, I'm just going to call that a plus c, different constant at the end. So it becomes x squared plus 4 natural log of the absolute value of x squared minus 4, and then plus c. That should be the answer to our definite integral. So now the other thing that we need to do in this section is some trig stuff. So I'm going to stop the recording on this so you can have enough to chew on here, and then go into some of the trig antiderivatives. But what I may do is I may wait for that one into class. So I think this is good enough for our Tuesday lesson. So we'll pick up on the trig stuff in class tomorrow. So work through logarithmic differentiation and odds and use substitution. So section 5.3, work the odds and evens for what's assigned on, going through number 29 would be pretty good, things of that nature. You don't have to do trig odds if you don't want to, because we will pick that up tomorrow. So that gives you about 10 to 15 exercises to work on. All right. See ya. Thanks.